Hello, this is a video on Bayesian versus frequentist approaches. You're probably most familiar with frequentist or classical approaches to statistics from your intro statistics class. So Bayesian will definitely be new to you, I think for the mass majority of you. And so this is a brief introduction to Bayesian approaches. So first, some misconceptions around p-values. So you're familiar with you need a p-value less than 0.05 to reject the null, and that's pretty much a heuristic in our field or a convention in our field, sometimes 0.01. Some misconceptions around p-values are: one, a significant result means that the effect is important. Not necessarily. You can have a statistically significant p-value, so less than 0.05 or 0.01 depending, and yet the effect size or the actual effect is quite small. And that's largely due to the fact that significance depends on sample size. So as your sample size increases, your likelihood of having statistical significance increases as well, given that you've underestimated your standard error. So in a standard t-test where it's mean sub 1 minus mean sub 2 over pool standard error, the larger your sample size gets, the smaller your standard error gets, which can make it look like that you have statistically significant results. It's a statistical artifact of that sample size. Misconception number two is that a non-significant result means that the null hypothesis is true. Not necessarily. You could just simply not have a large enough sample size, which would be an indication of a lack of statistical power. So those are the two main misconceptions there, which is why we emphasize effect sizes over just p-values as indications of statistical significance. So we look at effect sizes as indications of practical significance. So you have this distinction between statistical significance and practical significance. And so effect size is standardized means to measure effect size. So standardized means you can compare it across studies. It's not as reliant on sample size, so it's not as beholden to it. It's not as determined as highly by sample size, and allows people to objectively evaluate the size of an observed effect for your study. Effect size measures. There are several measures. The most common ones is Cohen's d, and that you use that in the case where you have a comparison of just two groups, so mean sub 1 minus mean sub 2. Pearson's r. You'll see that very commonly in regression. So an r squared value, so the square root of r squared is just r, and also sometimes in t, because t squared over t squared plus degrees of freedom square root is r as well. Odds ratios and risk or relative risk rates, you see that more in logistic regression and chi-square analyses sometimes as well. So, but those are just objective ways to compare across studies. So you look at effect size measures versus just statistical significance. So that has been the solution in classical or frequentist approaches, is to look to effect sizes, but there's also other approaches. You can do meta-analyses, etc., simulate in general. But the Bayesian approach is here to help us. Bayesian estimation. And so in Bayesian estimation, you have two main pieces of information. One is your prior information. So over here on the left, informative prior distribution versus uninformative prior distribution. And this is what we call your priors. So if you hear a statistician talking about, oh, what are your priors? He's talking about what is the prior distribution of your data, or what are your assumptions about that? And you can have two types of prior distribution information. You can have informative information, prior distribution information, or you can have uninformative or non-informative priors. So a non-informative prior would be like if you just said the chances of something happening are 50-50. So it's non-informative. If the outcome is yes or no, that is, like flipping a coin. So a non-informative prior. But it's obviously better to have an informative prior, meaning you have some sort of information to guide what you think is going to happen with your data. Okay, and then you have your actual data, so the data you collect and observe. So the informative or non-informative prior is like your model, what you kind of think is going to happen, and then you have your data that you collect, and then you estimate the posterior probability of that actually occurring. Okay, so you can see how your prior information can influence your subsequent posterior distribution. So in this example, we have someone's belief in their feelings being reciprocated for another person. So any person you can imagine, just imagine a person that you want to be, or in the past you wanted to be romantically involved with. So sometimes you have an informative prior distribution about that, like maybe you've interacted with that person many times before, or maybe you have non-informative prior information, like maybe you just kind of saw them across the room and you just love at first sight, and so you don't really have a lot of information on that person or you don't have a lot of information to base your belief in their reciprocated feelings, that they reciprocate feelings towards you. And so you can see clearly from this example yet again that it's better to have informative prior information regarding belief in reciprocated feelings. It's always better to have more information than less. And then your actual data. Your actual data would be like what your interactions have been or recently have been. So do they avoid eye contact with you? Do they avoid you in general? Do they smile when they see you, or do they just not smile? Are they more neutral around you? So it kind of depends what your actual data is going to be. And so you also have your prior distribution, whether or not you think they'd be interested based upon your prior information, based upon your interactions, etc. Your actual data, and then your posterior probability is like, well, what is the likelihood of that actually occurring? What is the likelihood of that belief in reciprocated feelings is accurate? Was the likelihood of that? So we're all kind of Bayesians in one way or another. We do our own internal Bayesian estimation of, well, what do we think is the probability of something occurring? Because it's not just based upon our data. We also use prior information of what we think is going to happen. So for instance, like if you find out that person is, I don't know, going through a divorce, or I don't know, whatever, your prior information would inform you maybe that your data isn't so accurate, so even if they smile at you and they're friendly, maybe they're going through a divorce, and maybe they won't be interested just based upon that prior information. So it's always a combination with human beings, and we're all doing Bayesian estimations of using our prior information, using our data, and then what is the likelihood of those feelings being reciprocated? So that's just an example. I think it's intuitive. And so this is Bayes' theorem, and basically it's the previous slide, going from the visual to the actual equation. The Bayes' theorem is the probability of A given B equals the probability of B given A multiplied by the probability of A over B. So in this case, the probability of our model given the data, and our model is the prior information, what we think is going to happen with our previous model. And your model could be the null, like, hey, nothing's happening. Or it probably could be like, oh yeah, some research hypothesis, yeah, something's going to happen. And given the data, and so equals the probability of the data given the model multiplied by the model, the prior, over the data. Okay, which gives us our posterior probability, which is the likelihood. So the probability of data given model is your likelihood, the likelihood of it occurring, multiplied by the prior probability over the marginal likelihood, which is whatever your most recent data before whatever event. And with that, you'll get a Bayes factor. A Bayes factor, you can state it two ways. There's the Bayes factor 0, 1 and versus the Bayes factor 1, 0. Okay, So when you do a Bayesian analysis, you'll get a Bayes factor score, and many times, sometimes they rely on just on confidence intervals. But in the JAS software, there's Bayes factor calculation. So a Bayes factor 0,1 is in reference to the null. So it's the likelihood of the data occurring given H sub O, the null, over the likelihood of the data given H sub 1. Or you can flip it around. The Bayes factor 1, 0, the likelihood of the data occurring given H sub 1 over the likelihood of the data given H sub O. Okay? And there really is no right or wrong here. You tend to see Bayes factor 1, 0 more just because people are interested in their research hypotheses more than they are the null. But there really is no right or wrong. It's just how you would state your outcomes. Okay, so Bayes factor 1.0 is in support of the alternative or research hypothesis. And for your Bayes factor score, it's going to be anywhere less than 1 to astronomically high, okay? And this is a general kind of interpretation guideline. So less than 1 is no evidence. That'd be like a non-significant p-value. 1 to 3 would be anecdotal evidence. 3 to 10, that's kind of where your marker should be. A Bayes factor value 3 or above means that you're cooking with heat, you know, so there's 3 and above, you can start to argue it. Bayes factor 1 to 3, that's, you would have to really argue for your model. It would have to be pretty darn convincing otherwise. You'd have to have other information. It would be difficult. But basically 3 is really the minimum. And then the higher the better, obviously. Then a Bayes factor of 0,1 is in support of the null. So that there's more evidence for the null versus not. And it's the same interpretation. It just, in this case, you'd be flipping it in support of the null. You could do it either way, though. The benefits of Bayesian approaches. You're comparing the likelihood of the null versus the research hypotheses. So it's not just about rejecting or not rejecting the null. You're comparing the null versus the research hypothesis. So they're basically competing they're competing against each other, competing hypotheses, and you find out what you have more evidence for. Unlike p-values, Bayesian methods are not confounded by sample size, so you don't have the sample size issue anymore because you're using the prior information with your data to calculate a posterior probability. With a Bayes factor value, you can report whether data were more probable or likely to occur under the null versus the alternative hypothesis. So what you would conclude, let's say if you have a Bayes factor of, I don't know, 3 or above, and it's a 1.0, means in support of the alternative, you would say that data were more likely to these data were more likely to occur under the research or alternative hypothesis over the null. Because remember, I'm talking about a Bayes factor of 1, 0. Now, if you were doing a Bayes factor of 0, 1, you would say something like data were more probable or more likely to occur under the null versus the research hypothesis. So basically, you're talking about competing models, those competing hypotheses. Okay? Okay, well, thank you. And this is a brief video on Bayesian estimation approaches versus frequentists, which you are familiar with from before. Thanks.